Alright, gang, here we go. This is for Chem 2 Unit 8, talking about phase changes. Should be lots of fun. In case you were worried, we're going to do some math in this video. I'm sure some of you guys were like, no, where's the math in the last couple of videos? Here's some. We're going to do some. Alright, so phase changes. Conversion from one state of phase to another. Alright, it's called a phase change, going from solid to liquid, liquid to gas, gas to solid, blah, 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 blah. Okay, and so, so as we do these things, we're either adding energy or taking energy away. It's either exothermic or endothermic process. So it's endothermic if we're adding energy to our process, okay? And so in this video here, these blue lines are our endothermic process. So to convert a solid to a liquid, we have to add energy to it, and that makes sense. If you want to melt an ice cube, you gotta add energy to get it to melt. Okay, if you want that water to eventually boil, you gotta add more. Okay, so here's the names of what we call them. Okay, melting or fusion is from is going from solid to liquid. Okay, all right, melting, fusion, and then vaporization, condensation is liquid to gas, and then sublimation and deposition from gas to solid. And so those are our six main phase changes. All right. Okay, here we go. So energy change and change of state. So we want to be able to quantify exactly how much energy it will take to make each of these changes of state happen. And so in order to do that, we come up with these tabulated values, and these are the names of those tabulated values. All right, the heat of fusion is the energy required to change a solid at its melting point to a liquid. Whoa. Heat is required to change a solid at its melting point to a liquid. All right, so that's the heat of fusion. So that's essentially you're melting it. Okay, so that's known as the heat of fusion. Heat of vaporization is the energy required to change a liquid at its boiling point to a gas. So you're vaporizing it, so you're starting with a liquid and you're changing it into a gas. And the heat of sublimation is the energy required to change a solid directly to a gas. So notice that in each of these cases, they're all defined as endothermic. All right, so they're all endothermic, so they'll all have a positive value, right? Because remember when we talked about thermochemistry, talked about endothermic versus exothermic process, we're adding energy to our system, and since it's coming in, it's got a positive value. All right, notice the units on these guys. All right, so heat of phase change, so fusion, vaporization, or sublimation, they're all in kilojoules per mole. So if we need to calculate it based off tabulated values, we always have to convert whatever it is into moles, and it's going to spit out kilojoules. All right, also notice that in all cases, the heat of sublimation is a lot higher than the other values, which makes a whole lot of sense, because like how often do you really things get sublimate? Not terribly often, right? And the main reason is because of how much energy it takes to make it happen. All right, and especially compared, like the other thing that that solids can do is turn into a liquid, and look how little energy it takes to go from solid liquid than it does from solids to gas. Okay, so anyway, and so that's kind of an interesting little bar chart there. All right, next thing we need to learn about here is these things called heating curves. All right, heating curves is a graph of the temperature versus heat. And remember, heat is energy flow. All right, energy flow. All right, and it's defined as Q. Remember, and so remember when we did MCAT. Remember MCAT? And it's essentially that. Okay, as one of these things here. So on this heating curve, all right, what we've done is we've got some. Looks like we're dealing with water here. Okay, so we've got water, some amount of water at negative 25 degrees Celsius. And then as we add heat, we're adding energy to this guy. All right, so heat comes in, okay, and the temperature of the ice goes from negative 25 and slowly gets up to 0. Once we've reached 0, we know that's the melting point of water. So once it reaches this point here, the ice is going to start melting. And as we're adding heat, more and more of our ice continues to melt until we get to this point. Now notice that as this phase change is occurring, our temperature does not go up. Our temperature holds constant until there's no more ice left to melt. Then once we're at this point, we're at complete liquid state. Only liquid water is left. And once that we get to that point, then our liquid water will start to raise temperature, and we'll keep adding heat and add heat until we reach point D, at which point we're at 100 degrees Celsius, which is, as you know, the boiling point of water. Okay, and so once we reach that point, any amount of temperature or heat that we add at that point is going to help us convert our liquid water into gaseous water or steam. And so from here to here, we have a mixture of liquid water and steam at the same time. And then once we reach point E, we are out of liquid water and we only have steam, and then our temperature can go up from there. Notice how much longer this part is here. It takes a lot more energy to convert our liquid water, okay, into steam than it did from ice to liquid. And that's all because of this idea of the fact that look at this amount of energy it takes to melt water versus the amount of energy per mole, kilojoules per mole, that it takes to melt it, or to boil it, excuse me. All right. Now, a couple other things we need to make sure we understand. When within a phase, so that's the blue lines, okay? So maybe we'll mark that blue lines, okay? The heat is the product of specific heat, sample mass, and temperature change. Well, let's add that here. So heat, okay? Heat is Q, and that's the product of the specific heat, all right? So specific heat, CP, times the mass of the sample times the temperature change, delta T. Now this should look really familiar to you. That's your Q is equal to, we can just rearrange this M CP delta T, our MCAT. So when we're within a phase change, when we are within a phase, okay, so just ice, so we're at these non-horizontal parts, okay, so the blue lines here, we can use MCAT to calculate the Q, all right? But once we're in phase changes, all we have to do here is multiply the heat will be equal to, and it says the product of mass or moles and the heat of fusion. So we'll use moles because that's what our heat of fusion is in. And remember this guy, and we'll call this delta H, all right? And this could be fusion or vaporization or sublimation, all right? Well, in a heating curve, we wouldn't have sublimation. It would just be because we're not going straight from solids to gases, all right? So fusion or vaporization here. And just to look at the units here, well, remember Q is energy, and so its units are going to be in kilojoules, all right? So let's think about the units here. N is in moles, all right? So moles. All right, and then this delta H value, we just saw in this previous slide that the units on phase change, okay, these heat of vaporization and fusion, are in kilojoules per mole. All right, so that's in kilojoules per mole. All right, and so these guys will cancel each other, and you'll just end up with kilojoules. All right, as we do our phase changes, we have to use the heat of fusion or vaporization, whichever one we need, okay, to do the phase change we're talking about. All right, and then and then we use MCAT for the non-phase change portions. All right, last little bit here is this idea of supercritical fluids. Okay, gases will eventually liquefy when you add a lot of pressure. Okay, so you know that a gas, that you can compress, so you can get those molecules really, really close together. And so the temperature beyond which a gas can no longer be compressed is called the critical temperature. And then the pressure needed to compress the liquid at critical temperature is called the critical pressure. All right. So supercritical fluids are beyond critical temperature and critical pressure. So if you had a pressure versus temperature graph, right, and then you reach this point here where you're at the critical pressure and critical temperature, beyond those 2 points, you're in the supercritical fluid area. Okay, and so anything beyond there is supercritical fluid. All right. And so here's some different molecules and their supercritical temperatures and pressures. Notice that it pretty much follows exactly those intermolecular forces and masses. The stronger the intermolecular force, the higher the critical temperature and pressure it can withstand before it kind of reaches that supercritical fluid state. All right. So now we're going to go through and we're going to do a couple problems here where we talk about being able to calculate delta H heat changes for these guys. And remember, they talk about enthalpy because at constant pressure, our enthalpy is equal to our heat. And so that makes our lives pretty easy. Okay. All right, so it says, what information about water is needed to calculate the enthalpy change for converting 1 mole of water at 100 degrees Celsius to water at liquid at 80 degrees Celsius. So we're starting with 1 mole of hydrogen, or water, 1 mole of water at 100 degrees Celsius, and then notice it's a gas. So we've got to convert 1 mole of water at a gas stage to 1 mole of water at the liquid stage. And remember that as our heating curve, right? So we started a solid, and then we became a liquid, and then we became a boiling point, and then we became a gas, like that. So we're like right at this point right here to start. We've got 1 mole of water at this gas phase. Okay, and so we want to convert it to this part here. We want to get to 80 degrees, right? 80 degrees at that point there. Okay, so maybe I should label these. There's a temperature, and this is our delta H. Okay, so so we want to know, well, what would we have to know to calculate? And we want to know, we'll go from this dot to this line. Well, to go from here to here, that's a phase change. We're going from a gas to liquid, so that means we need to know that delta H of vaporization, right? We need to know that value, all right? And then once we figured out, well, how much energy, what's the enthalpy change as we go from here to here, then we're at this point. Then we need to know the enthalpy change to go from 100 degrees down to 80 degrees. Okay, so this difference here. And so in order to that, we need the heat capacity of H2O liquid. Okay. All right, the heat capacity of the specific heat. And so heat of fusion, well, that's right out because we're not doing anything with solids. So we do need heat of vaporization, but it doesn't say anything about heat capacity. All right, specific heat of vaporization, and specific heat of water. Oh, but it's gas. We're not, that would apply over here. We're not over there, we're down here. So that, guys, so both of these are out, B and C, those are out. D, heat of vaporization, and specific heat of water. Okay, oh, so this is the one we need, right? Heat of vaporization, that's what we need right here, and the specific heat of water, now that's guy right here, so this is D, this is what we want. Okay, and the heat of fusion, well, that's out because we're not talking anything about solids. All right, so the answer there is D. Now let's do that same idea, but now we're going to like actually figure out the enthalpy change. It says, what is the enthalpy change during the process in which 100 grams of water at 50 degrees Celsius is cooled to ice at negative 30 degrees? All right, so let's draw our little graph one more time here. Okay, so we're starting at 50 degrees Celsius, and we're getting to negative 30. Why would they do that to me? Whatever. So we'll just say negative 30 is down here. Okay, and so 0, this is 80 apart, so 0 would be like right around here. Okay, and so we're starting up here. Okay, so we're going to start at this value. All right, right here at 0 degrees. And so we know that as we go, we're going to be having an enthalpy change, and the enthalpy will be leaving our system. And so we're going to be going down. Our temperature will be dropping until... it'll be dropping steadily. That'll be a straight line until we reach 0 degrees. And then once we reach 0 degrees, our liquid will start freezing, right? And so we'll have liquid water until all of the liquid has frozen, right? And so we'll be there. And then from that point, right, so it will go from here all the way down, and then we'll be at 0. Or we'll be at negative 30 degrees Celsius. All right, so just to remind ourselves, this is only liquid, this is liquid and solid, and this will only be solid. All right, and so that's kind of, so essentially what we're looking at is a 3-step. We need to do 3 different things here. And so remember, during these slanted parts, we're going to use, we'll just make ourselves a little note here, we're going to use MCAT during these guys. All right, MCAT, and then here we're going to use the heat of fusion. Okay, heat of fusion of water. All right, so yeah, so from 50 to 0, and you can make yourself a little note here, 50 to 0 degrees. So from 50 degrees to 0 degrees, our Q will be equal to mCp delta T. Okay, so our mass, well, that's easy. That's just 100 grams. All right, 100.0 grams. All right, and then our Cp, well, our Cp of water, so we need the Cp of liquid water, and they list that over here. We're going to have to hit the back arrow button several times here. So maybe I'll jot these down on a piece of paper so we don't have to. So it says the specific heats of ice, liquid water, and steam. So we need the specific heat of ice and liquid water. So Cp ice is equal to 2.03, and it's in joules per gram Kelvin. And the Cp of liquid water is 4.18 joules per gram Kelvin. All right, it says that there in the bottom of that second line. And then the other thing we needed was the heat of fusion, and so the delta H of fusion, right, and that's equal to 6.01 kilojoules per mole. Oh, shoot. Did you see what they did there to us? Look at this foolishness. See, this is the kind of thing you got to watch out for when you're doing questions, all right, when you're working with stuff. Notice that the specific heat is in joules per gram Kelvin, and these delta H's of fusion and vaporization are in kilojoules. And then obviously the grams and moles, and that one's easier to catch. But like the joules to kilojoules, man, that's evil. Who would do that? All right. Well, and I mean, really, the idea is that it takes a lot more energy to convert to make it change phases than it does to just change temperature. And that's really the reason, is because if you did the specific heats in kilojoules, you'd have like 2030. It's big numbers, and scientists don't like big numbers. We like scientific notation. All right, all right, here we go. We're gonna make it. Go, 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 go. All right. Whoops, too far. Okay. So we need so this is 50 to 0. So this is the heat, the specific heat of liquid water. Okay, and so that guy was in 4.18 joules per gram Kelvin, and remember Kelvin and Celsius are the same. Okay, so sorry. So because we're talking about a temperature change, the difference in 1 Kelvin is equal to 1 degree Celsius, and we talked about this when we did thermochemistry. So it doesn't matter that this is Kelvin or Celsius. I don't have to do a conversion. All right, so I'll just write degrees Celsius because that's what our temperature is in. All right, but it really doesn't matter because it's going to cancel. All right. And then our temperature change. Well, a temperature change is always final minus initial. Our final is 0, and our initial was 50. All right, so we'll be at negative 50 degrees Celsius, and that makes sense because the heat will be leaving, and so it should be a negative value when it's all said and done. Just to check our units here, our grams should cancel with our grams, okay, and our Celsius will cancel with our Celsius. Essentially, you don't have to worry about the formulas if you just worry about the units, because these guys, you look at your specific heats, and it's joules per gram Celsius or Kelvin, and you need just joules. It should be easy to say, oh, I'm just multiplying by grams, and I'm multiplying by Celsius, and then you're good. All right, so we'll take 100 times 4.18 times negative 50. All right, and we'll go ahead. I got 20,900. Let's go ahead and convert that to kilojoules on the fly here. And so that would be negative 20.9 kilojoules. All right, so that's our Q from 50 to 0. Now we're doing our phase change. So this would be freezing. All right. And so from freezing, we're going to use the delta H formation, right? So our Q is going to be equal. Remember, it was equal to the number of moles times the delta H of, in this case, it's fusion because we're freezing, all right? Well, that presents a problem, right? Because we need the moles, all right? So we got to convert our grams of water to moles. So we got 100.0 grams of water, and we got to convert that to moles, all right? So grams of water go on the bottom, moles of water go on the top. All right, so for every 1, and we won't do the molar mass by hand. We just know it's water. So 100 divided by 18.02, you get 5.493. Right, 5.49. Oh, 4, 5. Oh, I skipped a number. 5.5493. 5.5493. And notice I'm not worrying about sig figs at this point because I don't want to round for sig figs early. Okay, it might throw things off. So this is the number of moles of water that we're worried about. All right, so that's our moles. So 5.5493 moles. All right, and now we use the delta H of fusion. Good thing I wrote it down earlier. All right, so that's our 6.01 kilojoules per mole. All right, so notice again, our moles just cancel. All right, and we're just left with kilojoules, which is exactly what we wanted. So we'll take our 5.5493 times 6.01. We get 33.35 kilojoules. All right, so it should have 33.4 kilojoules. 3 sig figs because of this guy here. All right, 33.4 kilojoules. And so this should also be negative, right? Because because we're going backwards, energy's leaving, right? So it'd be negative 33.4 kilojoules. And then last step, we're going from 0 degrees to negative 30 degrees. All right, and so we'll use our MCAT again. So Q is equal to mCp delta T. All right, so our mass of our water is still 100 grams, 0.0 grams, and our CP of ice is 2.03 joules per gram degree Celsius. All right, and then the change in temperature is at negative 30 degrees. Final minus initial 0, or final was negative 30 minus initial, which is 0. All right. So we'll take 100 times 2.03 times our negative 30. We get negative 6,090. So that would be negative 6.09 kilojoules. All right, so the total change would be negative 20.9 plus, right, and we're adding in negative 33.4 and negative 6.09. Okay, and it looks like we're going to have to round to the hundredths or the tenths place, so negative 20.9 plus negative 33.4 plus negative 6.09. And so I got negative 60.39, but we got to round to the tenths place because of these two guys here, right? So it become negative 60.4, and we're at kilojoules. All right. So in order to the enthalpy change to go from 50 degree water to negative 30 degree ice would be 60.4 kilojoules. We'd lose 60.4 kilojoules. So that's it for phase changes. You know, obviously, like a lot of the stuff's review, a lot of the vocab like should not be new material. We talked about a lot of it in Chem 1. You probably learned a lot of it in like middle school, but the math is probably new. So this is the part we really got to focus on because these math problems can be kind of tricky because there's a lot of things to think about. Where is my phase changes occurring at what temperatures, and so what state of matter am I going to be at? Especially water is easier because we're used to thinking about water. Water freezes at 0. Boils at 100, but we could do it with anything, right? And so once you do that, you got to start thinking about, well, where is my phase changing occurring, so on and so forth. Anyway, let me know if you have any questions. Go ahead and do your practice problems, and I'll see you on the flip side.